Hi, welcome to another edition of linear algebra. We were talking about matrix algebra and the properties of matrices as far as addition, subtraction, multiplication, and transpose were concerned last time. Let's go ahead and do a couple of problems in this area and see how we can make use of the stuff we have learned so far. So, I have two problems for you here. Three matrices are given. M1, M2, M3. And then there's a target matrix. We want to know if this matrix is a linear combination of the matrices we already have. Another way of expressing the same problem is this target matrix in the span of M1, M2, M3. So its span was a set of linear combination. Second question is, after we answer this, we ask, well, what if I had another target matrix? How would you answer that? And then say I change again and change again. So part B says describe all matrices that are linear combination of M1, M2, M3. What are all matrices we can put in terms instead of T and still hope that it is a linear combination of these three. Another way of describing the same question is explain what is the span of M1, M2, M3. Okay, how does this relate to the topic of discussion that we had? At the beginning of a semester, we talked about linear combination, but that was linear combination of vectors. Now we have matrices, and we are asking exact same question, and we want to know how does this get to be answered. And it turns out to be exactly the way we did before, just the format of it looks different. Concept of span is also very similar to what we had before. So remember, we are looking at the matrices, and then we introduced a new set of operation with them, that was the dot product and so on. And then we listed the properties, sometimes as the axioms of matrix algebra. The significant new thing was with respect to multiplication. What we define to be multiplication is entirely new thing, even though we are using the word multiplication. So we said we needed to go ahead and list which one of our algebraic steps are still valid and which ones are not surviving the process. Let me remind you again what we have for matrix multiplication. So in matrix multiplication you have two matrices, first and the second, and the way you define this multiplication is as dot product of the rows of the first and the columns of the second. So for example, first row here is 2, 3, minus 5. First column of the second is 4 minus 2 minus 2, and you arrange a dot product between this green and the purple. Here is how we do the dot product, and we get a number out, and then that number gets to be written in a location whose row is the row of the first and whose column is the column of the second. So for example, if I wanted to go to say row 2, let's see if I can convince this slider to move, and say column 3. Okay, so I went to row 2 now. Row 2 is colored green, column 3 is colored purple, and the answer comes out and is sitting at row 2. It inherits it from the first, and column 3, and it inherits it from the second matrix, and that gets to be written here. What's written here is the result of this dot product, and this complicated operation, we call it multiplication. Okay, an entirely new creature is built on our arithmetic, but we just call it multiplication. And then we say, well, many of the properties of multiplication we are used to from elementary school are still there. Most notable among them is that the associativity of matrix multiplication is still there. Notice that this is no ordinary property to just expect out of thin air that it has to be there. It has to be actually established. We didn't. We left it to you or for a more advanced class to go through this step, but you can take three matrices, keeping them small size like 2 by 2, and multiply them out to actually see that you end up with the same answer. So we talked about transpose and how transpose deals with plays along with multiplication and powers and so on. And and then in the process we said two properties are lost. So not everything from high school goes through. Commutativity is lost. That's one thing. And the zero factor theorem is also lost. So we had two casualties of this new adventure that we have. Now we are going back to stuff that we had at the beginning of the semester. And we say, well, some of these can still be applied to matrices, exactly same style as before. And here we are just getting used to how this is being done. So first question again, is we have a bunch of matrices, and then we have a target matrix, and we are asking, can you make this target matrix from those items that you were given? Make how? Make in terms of linear combination. So what does that mean? It means I make a linear combination of these things. So I have like say A times M1 and B times M2 and C times M3. So just like cooking, you take a little bit of this and a little bit of that and a little bit of that, you add them together. Well, how is this recipe supposed to be created, ABC? Well, the recipe is supposed to be done so that out comes this target matrix. So that's what we mean. T is a linear combination of these other things. Or when we say T is in the span of this, it means such an activity does result in T. Well, now what? Now the question is, so in part A, essentially what, well, let's call it this A. Of course, it's not that A. We don't make such a mistake. So let me just change it in. So, so we want, we want to find numbers A, B, C such that this is true. Well, we just go ahead and enter all of our data. So I want to find A such that when I multiply it by 0, 1, minus 1, 0, that M1 is that they gave me, and B times M2, M2 is just identity 1, 0, 0, 1, and C times M3, M3 is just everybody is a 1 and 3 is 1, and I want to be able to create 1, 4, 2, 1. Well, this is an ordinary equation but written in a matrix format. So it's still true that if I take A multiplied by the first, well, let's go ahead and just actually multiply this thing out. This is 0, A minus A, 0. And this is going to be B, 0, 0, B. And when I multiply by C, just everybody becomes C. And then I want to make 1, 4, 2, 1. Well, how do you add these things? So let's just go add them. How do you add them? You just add them. 0, B, and C, you add them. And then you get what? Well, 0, B plus C. And then second entries, well, let me also color the right hand side to say who they are going to be equal to. So I have A plus C, and then see, we don't run out of colors. This is, they are going to match each other. So I have minus A plus C, and this is a bit darker, so let me put it underneath. So it's B plus C. So this is the sum of left hand side and the right hand side. Of course I want to match it against 1 4 2 1. So the idea is that when two matrices are equal, of course their corresponding elements are equal. So we make an equation like that. So I have B plus C has to equal to what? 1. A plus C. So let me, while I'm doing it, let's line them up properly. And the third equation is minus A plus C, and that has to be 2. So that is saying the green and the green are matching. And then of course the last item is B plus C has to match 1. So the requirement that we have T express T as a linear combination of these matrices, it just turns into a matrix equation all by itself. Now, well, this is a matrix equation. We go ahead and solve it. You remember from beginning we had that grand theorem saying that when you have a linear system, either it has no solution, or it has a unique solution, or it has infinitely many solutions. Which one would this be? Well, in any case, you have to actually dig in to see what happens. You cannot foretell from outside, but sometimes you can make general remarks. What general remark can we make here? Is this a reasonable question to ask? Meaning, is it possible to make a matrix out of 3 other matrices? We come here and see we have 4 equations, but we have 3 unknowns. 4 equations in 3 unknowns in general would not have an answer. It would be impossible. So like in general, if these 3 matrices were just some random matrices, or some field measurements, and this was some other random matrix, and the question was, is this expressible in terms of those 3, and we were willing to bet and quickly go to something else, our bet would be no, it doesn't have a solution, because we have 4 equations and we have only 3 degrees of freedom in between them. So in general, such a question will have an answer of not possible. But when we look at some specific case, or well, perhaps in a specific case maybe something fluky happens and then it is possible. So for example, we clearly see something fluky going on here. So the first and the last equations are the same thing, so one of these things is redundant. You can just cross it out. You have 3 equations, and 3 equations, 3 unknowns generally has a solution. So those are general remarks. In any specific instance, what do we do? Well, in any specific instance, you sit down and solve the equation. There is no shortcut to that. So in this case, we go ahead. You can, so we say, okay, this you can simplify to B plus C equal to 1, and A plus C equals to 4, and minus A plus C equals to 2. This is a rather friendly equation. For example, when you add these two, we can set aside everything we have learned about Gaussian elimination and such. Go back to high school Algebra 2. You can do this thing out of that. So for example, when you add these two equations, you get 2c is equal to 6, and so the value of c comes through easily. So when you have c is equal to 3, you put here, and then of course you get your a to be equal to 1, and if c is equal to 3 and your b is equal to minus 2, and then that is the recipe. The recipe says take one of this matrix 0 1 minus 1 0, and take minus 2 of the second matrix 1 0 0 1, and take 3 of the last matrix 1 1 1 1. So here's our ABC. When we multiply by these numbers, we are supposed to get 1 4 2 1. So do we? It's always a good idea to double check. So the 0 minus 2 and 3 is 1, and then 1 and 3 is 4, minus 1 and 3 is 2, and then minus 2 and 3 is 1. So we have verified, so this is indeed true, these are equal to each other. Okay, so that's answer to part 1. So in general, if these were random numbers, when we were pressed for time, we were going to bet, we would have bet it's not possible because 4 equations and 3 unknowns, you cannot satisfy it. But in particular situation, perhaps you could, depending on what kind of special numbers you have. And this was like a lucky coincidence that we could actually do such a thing. So next question up is the following. Next question is, well, what are all the other lucky ones? What are all the other target vectors you could make from these 3? That's in part B. It says describe all matrices. What else can I have in terms of T that would have the same property, that you can actually build it out of these things? What else is possible? So now in this problem, if our matrices were larger or our numbers were less friendly and such, you remember we have a lifesaver here in case you want to try that. That is also available to you. You can always use, let me reset this thing. So okay, so for reasonable size matrices, as far as I would say even 10 by 10, you can handle it on this. But most problems are such that you can actually do it by hand, and you are encouraged to do it both ways. Do it by hand and then do it by also that web app and see how it happens. So in part B, the question is what numbers can you put here so that you can solve this thing. Again, remember that we were saying that in general this would not work. You cannot resolve a matrix in terms of these 3 that are given to you. But now the question is, what is it that you can do? So what we do is, one possibility for this thing is to say, okay, I want to describe what numbers I want to put here. So I'm going to go ahead and make those things also variables. I call them x, y, z, t, or whatever. And then ask myself, what should be true about the x, y, z, t, such that the question again has a positive answer. So part B of this puzzle is so part B, describe span of. So this is how we technically talk about this thing. Describe this span. It means describe x, y, z, t so that t is a linear combination, same as before, linear combination of m1, m2, m3. So again, same as before, a m1 plus b m2 plus c m3. I want it to be equal to t. But what I want here is not primarily just a, b, c. Primarily what I want is to describe t so that it has a solution. So let's go ahead and do the same thing as again. So it's exactly like this, except that instead of 1, 4, I had 1, 4, 2, 1. Now I have x here, y here, my z dangerously looking like it, z here, and a t here. So if I replace 1, 4, 2, 1 and replace them by just 4 numbers, x, y, z, t, would it have a solution? You can immediately bet that it wouldn't. It's rather obvious. Let's go ahead and write it. So my equation now reads just like as before. Let me rewrite it. So b plus c equals to I want it to be x, and then a plus c, I want it to be y, minus a plus c, I want it to be equal to z, and then b plus c, I want it to be equal to number t. So the question is for what? For what values of x, y, z, t does this system have a solution? Does this system have a solution? At least one solution. If it has more, that's fine, but we want to rule out the cases where it wouldn't have a solution. Before we bog down into details, can you tell me anything particular about x, y, z, t that should be true for us to even investigate, to even go after finding ABC? So here we pointed out to something fluky that has happened that made us actually have a hope of finding ABC, and that was the first and last equation were the same. So we dropped the last one, concentrated on the first three, and I got my ABC. I come here and say, well, obviously if x and t are different numbers, you are already looking at inconsistent equation. For example, if this is 5 and this is 7, when obviously you cannot find a b and c such that b plus c is 5 and the b plus c again is 7. So obviously we require that x must be equal to t. Whatever matrix you are looking at, the elements on the diagonal have to be the same for the process to work. But is that enough? The question is, so we obviously do need so what is required is that x is equal to t. Otherwise, obviously, you have inconsistent equation. But the question is, so this is, we call it in mathematics, we say this is necessary. It's necessary for x to be equal to t. But is that sufficient? Meaning, if x is equal to t, then can I go ahead and do everything? Again, you can go ahead and do this by that web app or a lot of discussion, but the problem's quite easy to do as we did before. So let's call this thing equation 1, equation 2, equation 3. So if I go ahead and add equation 1 and equation 2, my a's cancel. I get 2y, excuse me, 2 it's a huge eraser, 2c is equal to y plus z. So your c is y plus z divided by 2. And once you have your c, you can go ahead and find, so a becomes y minus c, so a becomes y minus, here's your c, you take a common denominator, so it becomes 2y minus y plus z, clean this up, y minus z over 2, and then what else? So well, b is also equal to x minus c, so your b is x, which well, x is x, c is this quantity, x plus z over 2. You can leave it like that, or you can write it this way, however you want, that's fine. So if you give me x, y, z and you insist that t has to be same as x, then I can give you a, b, c such that the linear combination of m1, m2, m3 does give you your t. So what this means now is that my a turned out to be y minus z over 2. This is my a. If I multiply it by m1, who was m1? m1 was 0 1 minus 1 0 plus plus b times so b is this 2x minus y minus z over 2, and our m2 this was m2, just identity, 1 0 0 1, and then so this was b m2, and then c y plus z over 2 times m3. You remember m3 was just all ones. This was our m3. This was our m3, all ones. So what did we want to do? We want to create that matrix which was x, y, z, t, but we said we can do this thing if x and t are the same. So I need to, instead of this thing, I need to insist this is exactly the same number as that. If that is the case, then such matrices can be made out of m1, m2, m3. So the coincidence that makes this thing possible is for these entries to be the same. If they are the same, then yes. Otherwise, no. If they are the same, how do you actually make it? Here's the recipe. Here's a cooking recipe. How do you mix these things to create that? But so each problem can be approached like this. Now again, if the numbers you are working with is bigger than this, bigger matrices, unfriendlier numbers and such, you can always come back to the to this and do the problem that way. So maybe so how do you use that web app? Bring everything to the left hand side. It's going to become a humongous equation of b plus c minus x equal to, let me move this thing here. So this is the location for a, b, c, x, y, z, t. So by now we have 7 variables hanging around our neck, and now we have next equation a plus c minus y equal to 0. Next equation is minus a plus c minus z equal to 0. Last equation reads like what? B plus c minus t equal to 0. Okay, this is the equation you're solving. So if you wish, you have 4. If you want to insist on having a right hand side, even though it's not necessary, this is all zeros, but if you want to keep it, 3, another 4 is 7 with the right hand side, 4 by 8. So you can open that web app if you want. You can convert it to a 4 by 8. So this will be 4, and then this is going to be very big, 8 columns. Then you can put your entries here. So this was still 0, 1, 1, and 1, and everybody else was 0. Next, this was 1, 0, if I remember, this is 1, and then this was for x, this is for y. Then we go, and then I have minus 1, and then 0 and 1, and then I have this was for x, y, this was for z. Last equation was this was for C, if I remember correctly. This is for T. And right hand side here, the 8th column really no use, because it's all zeros. Whatever you do to them, it will be all zero. But just to remember, this is the right hand side of our equation. Then what? Then we want to solve this thing, so we want to have a pivot here. So let's exchange these two rows. Okay, well, I forgot, we have to actually first go back to the matrix. So we are done with editing, everything is finished, so I resume. Okay, now I exchange these two rows so that entry is a pivot. Now I use this to eliminate. I go and eliminate this entry. Now I use this to eliminate this entry. I can make this thing into a 1 just to make it standardized. Okay, now here is the this is the echelon. If you want to simplify further, be my guest. Like, for example, make this thing row reduced echelon. Then I can use this entry to eliminate that. Use this entry to eliminate that one. Use this entry to eliminate that one. So now we have a perfect ones on the diagonal. Now the last equation reads like what? This is if you remember, this is A, B, C, then X, Y, Z, and T. This becomes T. So the last equation here reads like X minus T has to be equal to 0 for our equation to be consistent. X minus T has to be equal to 0. What does that mean? It means X has to be equal to T. That is exactly what we discovered here, that X has to be equal to T. So on that web app, how do you see this? The way you see it, the problem in the web app is that you have to remember what are these columns for. So you remember this was A, B, C, then X, Y, Z, T, and this was your right hand side. So that is how they are labeled. So in the last equation, if you write it in a traditional format, how does it read? It reads X minus T is equal to 0. Well, that's what it means for X to be equal to T. And then what? Well, this was for C. This is for C. It says C is equal to 1/2 Y plus 1/2 Z. That's what that means. And so on. This is for B, and this is for A. So you have to practice to make sure you can use that web app, understand what it does, and then be able to actually solve your equation. Okay, so what was the purpose of this lecture? We said now we can many ideas we had at the very beginning of the semester for vectors can be extended to matrices. In some sense, matrices are vectors. It's just that they are folded in this funny rectangular way. But if you take all of these things and string them out as a column, as a row, they are just like vectors. And we had the combination of vectors before in span, so same thing applies here. Okay, you're going to have a few exercises on this, and then we are going to go to the next topic in the next lecture. What would be the next topic? Let me remind you. So by now we have said quite a bit about these. Next, we have to prepare ourselves for division and issues with respect to that. Once we handle that, we are going to take a look at the advanced stuff for the end of semester. we are going to do so-called Eigen Analysis, so that the case of power and of functions can be handled. What do you mean by functions? We want to make sense of exponential of a matrix. Why do you want to do that? Again, because that's how to explain vibrations. One of the thousands of applications of this course, linear algebra, is in the case of explaining vibrations, and that's what we are going to see over there. And we need to understand what happens with powers, and that's going to require eigenanalysis. Okay, so that is going to be our new section starting in the next lecture, and until then, good luck and God bless.